For chemostratigraphic studies, sampling practice is to be understood. The core and the cutting samples in case of a drilling exercise should be taken at 3 to 5 feet interval and at every 10 feet interval. For the core, the data can be taken at 3 to 5 feet interval. The cutting samples can be taken after every 10 feet. One has to be alert with the core and the cutting, and which one is more reliable, core and cutting, can be discussed. There is a misconception that the data quality is always better in cores than in cuttings. Cores have better depth control than chips. This is to be understood. When the core is picked up in the process of drilling, some chips might fall down. So, the core accurately represents the depth range Z1 to Z2, whereas the chips that are falling down from Z2 depth, it can come to Z3 depth. So, if the cuttings are picked up, those cuttings may not represent the true depth. So, in that way cores are preferred. Further, the cuttings and the chips are more contaminated than the cores. Contamination comes from the additives that are used during the drilling program. Therefore, in case chips are used, they should be thoroughly washed so that the additives are completely removed. It is a common sense idea that for lower resolution of studies, we need less dense sampling, and for higher resolution of studies, we need denser sampling. Suppose this is a litholog and I need a lower resolution studies. In that case, my samples can be widespread, can be far away from each other, whereas in case of higher resolution studies, sampling should be more dense. This is for higher resolution of studies. Although I right now said that core can be more preferred, but there is another argument that cutting samples data can be more reliable than core's chemical data, because the cutting samples data can show smooth pattern of geochemical variation, and that can be useful for the chemostratigraphic correlation. In fact, one cannot blindly rely on the core or on the cutting. One has to ensure that the core or cutting, whatever is picked up, from its actual depth from where it is taken out, and second point, it should be free from contamination additives which are added during the drilling program. Sometimes despiking of data is required. This involves reduction of anomalies, high or low. Suppose we know that expected normal value is x, the compositional data, and we have got y, where y is either much more than x or y is much less than x, and this magnitude is abnormal. That means the data has been spiked. To avoid this spiking, we need despiking process. This is a process by which the y value that is obtained is reduced to or changed to y0 amount or y0 dash amount. This is the meaning of the term despiking. This is the point that I was telling in the previous slide, that the cutting samples data is more reliable than the coarse chemical data, because the cutting samples data shows a smooth pattern, and that is useful for the chemostratigraphic correlation. An example is taken from the Saudi Arabia, where the core samples are studied to find out the ratios ZR divided by CR, ZR divided by Ti, and potassium divided by aluminium. And once they are plotted, much of the spikes are available, and these spikes make it very difficult to correlate chemostratigraphically. So, in such a situation, cutting samples would be important to see what kind of data comes out. Now, the question comes, suppose both the core and the cuttings are uncontaminated, or whatever contamination was there has been removed by chemical processing. In that case, do you think that the core and the cutting can give different kind of data? While sampling, avoid conglomerates and breccias, because these are the rock types which are much heterogeneous. Results can vary significantly over a short length. If this is a sample of breccia, then from here to there can be too much variation in the chemical composition. So, what is recommended if we are dealing with a conglomeratic section, do sampling immediately below it or immediately above it. That is what is said here. Same with the breccia. Breccias are angular rock fragments which can be produced due to faulting. And in case one cannot take the samples above and below the conglomerates and the breccias, then at least sample the matrices. In case of conglomerate, big class, and then there are smaller matrices here. Pick up this matrix for the geochemical studies. Avoid the cores containing rubbles. Very big particles can be found in cores. Avoid them in studying the geochemistry. These rubbles can come as possibly drop stones. These can be drop stones. Denser sampling needed across stratigraphic boundaries. Suppose we already know that here between rock type A and B is a stratigraphic boundary. So, the sampling was done at regular interval, but near the A-B boundary the sampling density has to be increased, as I have shown here, that more number of points for sampling. So, at A-B boundary, if a stratigraphic one do more sampling. Just to give an example of a stratigraphic boundary, unconformity is one kind of stratigraphic boundary. While sampling, choose a representative part of the rock. That means, if this is a rock section I am watching and I am finding a uniformity, and then here visibly there is some other rock particles, mineral grains, then I will choose sampling, of course, from here, because this is a representative section. I will not go to choose the sample for geochemical analysis from this portion. Always add detailed description of the rock, such as the color, grain size, the primary structures, the minerals, even if it is a routine work, so that the future geologist can understand the situation and accordingly take decision. It may be possible that the driller has provided us samples without numbering. Of course, they are to be avoided. Samples without numbers means we do not know from what depth range they have come. Some kind of washing might be involved in the while handling the core and the chips. Sometimes it may be important to avoid the washed samples. Unwashed samples sometimes give better information about the rock's chemistry, because washing sometimes introduces new elements within the rock. How much rock should be analyzed? Nearly 8 gram or more, or 2 to 3 centimeter cube or more volume of sample are required from cores or per spot in the field. They should be kept inside plastic packet, and on the plastic packet the number should be written. Now, these numbers are the average numbers. Avoid inked or painted part of the core in sampling. Of course, this is to be done so that the contamination can be avoided. Contamination can happen from the painting or the inked portion. When the core is picked up, if possible, avoid outer 0.5 centimeter of core, so that the drilling related additives can be avoided. This is the outer portion of the core, and this is to be avoided in the geochemical analysis. We need to have some idea about the drilling mud additives. Elements most commonly associated with the drilling mud additives are Ba, Ca and Sr. So, in the sample, if we find a spike of Ba concentration, Ca concentration and Sr concentration, a chance exists that the drilling mud additives have been chemically analyzed. So, one has to be careful if such spikes are found. But a Ba spike, Ca spike and Sr spike is also possible naturally within the rock. So, that also is to be remembered. When the Ba concentration is more than 20,000 ppm, the effect of additives seem to have gone within the cuttings. This is coming from the previous point. Reprocessing, that means re-washing of sampling, is recommended, but at the same time ensure that washing does not itself introduces other elements. Relatively low level of barium, such as within 200 to 1000 ppm, is expected in the core samples. This is just an average number and it may vary from rock to rock. If we do not take care of the high barium, if we cannot avoid such samples, then in the XRF analysis it creates a trouble. The calcareous additives can contaminate samples with calcium and strontium. If a set of samples were derived from quartz arenites with no record of carbonate cement, no record means what? Not seen in hand specimen and also not seen under an optical microscope, but it produces 10% of calcium, say, now that will mean possibly that calcium has come from the drilling additives. This means that hand specimen observation and microscope observation are indispensable part of the chemostratigraphic studies. I mean, they are the supporting work and they are very important. In the XRF studies, elevated proportions of drilling additive bearing calcium, for example, calcium more than 9% and less commonly barium and strontium, may result in dilution of low concentration trace elements to the point at which they occur at levels below the limit of detection. So, these points are to be kept in mind. Heavy mineral stratigraphy is an important branch of chemostratigraphy. For that, I have already delivered NPTEL lecture, you can have a look. Binary diagrams are of great use in chemostratigraphy, where Ti percentage, thorium in ppm, Ta in ppm, Nb in ppm, Ga in ppm, Rb in ppm are plotted along x and y axis and the rocks data are plotted. Similarly, Nb in ppm, Ti percentage, thorium in ppm, Ta in ppm, then thorium in ppm and Zr in ppm, and then potassium percentage and Rb in ppm, aluminum percentage and potassium percentage, calcium percentage and Si percentage, Al percentage and Ga in ppm, Ca percentage and Mg percentage, Al percent and Si percent are of great use. We may find positive trend or no significant trend in data set. You can also find negative trend. So, in these binary plots we can find ppm versus ppm plot of different elements. We can find ppm versus percentage plot of various elements, or we can find percentage plot along x and y axis for the various elements. Through binary diagrams, we establish the mineralogical affinities of the elements. For the lithology of the sedimentary rock, some general rules can be given. Si by Al ratio is less than 5 can indicate we are dealing with claystone or shale. Si by Al ratio between 5 to 6 can indicate it to be siltstone. Si by Al ratio within 6 and 8 can be coming from an argillaceous sandstone. Si by Al ratio more than 8 is coming from non-argillaceous sandstone, and calcium percentage within 7 to 15% means it is a calcareous. So, from here to here basically we see that it is increase in Si-Al ratio and the composition changes from shale towards non-argillaceous sandstone. Argillaceous component comes from the clay or shale, that component being reduced. But here is a word of caution that this is not the fixed criterion. So, be careful in using such information. In the literature there are many such statements available, along with the word of caution that such ratios cannot alone decide the rock type. So, given a chance, always see the rock in hand specimen and in thin section. The elemental ratio can also distinguish various kinds of sandstone. For example, if we plot log Si divided by Al along the x axis and log sodium divided by potassium along the y axis, then arkose, which is a feldspar rich sandstone, lith arenite, and then subarkose, sublith arenite, and then quartz arenite and grey wacke can be discriminated. There is another diagram of log Si by Al and log Fe by K. So, here the parameter has changed. Earlier we are plotting sodium by potassium, here it is Fe divided by K. Si by Al has remained the same. In both places we have taken log. We are writing log, which means to the base 10, and here again we can define arkose, subarkose, quartz arenite, sublith arenite, lith arenite, wacke, shale, Fe shale and Fe sand. To identify the source or the provenance, these are the list of ratios which become very important. We note certain elements always in the numerator, such as Zr. We do not see Zr in the denominator in the list, and there are some elements which can occur either in the numerator or in the denominator. For example, Ti comes in the denominator in this ratio, whereas here Ti comes in the numerator. You may find some element which always occurs in the denominator and never in the numerator. Can you locate them? There are less commonly used ratios in chemostratigraphy that can give much less information about the chemostratigraphic boundaries, but they can be useful to provide information on the element, mineral links, weathering and depositional environment, and these are the ratios. One can group elemental ratios which can have multiple purposes. They can indicate provenance depending on the situation or the depositional environment or weathering and diagenesis. We are going to see the chemical alteration indices. Most chemostratigraphic schemes are associated with elements and their ratios, and these are associated with changes in provenance, but is equally important to state parameters that reflect subaerial weathering. Since the term weathering is coming, unconformities obviously come to the mind, and the weathering surfaces can be correlated using the CIA. Chemical index of alteration is aluminium divided by Al plus Ca plus Na plus K. Here a star is given, so Ca star is explained. It is the proportion of calcium concentration in the siliciclastic fraction. CIA indicates intensity of subaerial weathering. It is same thing what is said here. Unweathered igneous rocks and average shells yield CIA less than equal to 50 and 70 to 75 respectively. Unweathered igneous rocks give CIA less than or equal to 50, and the average shells give CIA 70 to 75. Residual clays with high kaolinite or gibbsite content produces CIA up to 100. But it is also to be stated that CIA alone cannot predict the rock type. It can act as a supporting evidence. What is the basic theory involved in this CIA? During weathering, calcium, sodium and potassium are released, causing a preferential increase in aluminium and the CIA value. In this formula, imagine within a rock erosion happens, then that actually removes Ca, Na and K. Once this is out, that means numerator divided by denominator here, this value is reduced. As it is reduced, the ratio actually increases. So, more intense weathering will indicate higher value of CIA. Just like CIA, a weathering index Wy can be defined. Here it is aluminium divided by Ca plus Mg plus Na plus K. So, what is the difference between CIA and Wi? The difference is that in the denominator of Wi, Mg is present, which was absent in the CIA, and here only Ca is written, not the Ca star. Mg and Ca commonly exist within siliciclastic minerals. Wi increases with increase in weathering. As in case of CIA, so also in case of Wi, as in weathering increases keeps going on, Wi value keeps increasing on the residual rocks. One of the serious problems in the formulation of CIA and Wi are that it is often difficult to correct the proportion of calcium associated with carbonates and phosphates. Although the term calcium is found in the definitions of CIA and Wi, finding out calcium associated with carbonates and phosphates, such rocks, becomes most difficult. So, CIA and Wi have limitations in their use. There are other CIA, for example, this one, but as I am writing, it is not free from assumptions. One cannot blindly use. One has to see what are the applications, what are the drawbacks, and accordingly use carefully. When calcium percentage is more than 7, the below formula can be used. CIA equal to Al divided by Al plus Na plus K. That means calcium is dropped. Wi is equal to Al divided by Mg plus Na plus K. That means in such cases, calcium is dropped from the formula. In such a case, and what is that case? Ca more than 7%, what is done? Ca is dropped from the formula. Just watch this. Here in defining Wi, Ca in the denominator, and in defining CIA, Ca star in the denominator, whereas here when calcium percent has increased, we drop Ca from the formula. We do not drop Al, Na, K or Mg from the formula. There are other indices, but they are less commonly applied in chemostratigraphic studies. CPA, chemical proxy for alteration, Al divided by Al plus Na multiplied by 100. CIW, which is Al divided by Al plus Na plus again Ca star multiplied by 100, that means expressed as percentage. PIA, plagioclase index of alteration, is Al minus K divided by Al plus Ca star plus Na minus K multiplied by 100. Here Ca star stands for the silicate bound calcium. ICV, index of compositional variability, is Fe plus K plus Na plus Ca plus Mg plus Mn plus Ti divided by Al. So this is a formula ICV where aluminium comes in the denominator. Aluminium in the numerator and denominator both in case of CIA, aluminium only in the numerator in Wi formula, aluminium both in numerator and denominator in the PIA formula, and in case of CIW, aluminium both in the numerator and denominator. In case of CPA, aluminium comes both in the numerator and the denominator, whereas in ICV, aluminium does not come in the numerator. While dealing with elements and their ratios, we need to remember that element concentrations can be normalized to chondrites by dividing the measured concentration of each element in a sample by its average abundance in a standard chondrite meteorite. This process is often used for the rare earth elements. For which elements we do chondrite correction? The answer is the REs. They help to visualize the relative enrichment or depletion of elements in a sample compared to the primitive solar system. We consider that the concentration of elements in the chondrite represents that of the primitive solar system. And if we use the resulting normalized values in creating diagram, in creating graphs, it can be called chondrite normalized diagram, and such diagrams are useful. Normalized concentration, what does it mean? As I was telling, it is a concentration of element in the sample divided by the chondrite abundance, what is found in the chondrite. Let us look at few of the chondrite values. For EU, it is 0.0685 ppm, SM is 0.183 ppm, and GD is 0.252 ppm. How the different elemental ratios can be used to define the different zones or the chemozones and their divisions, I am going to explain. Consider we are finding a portion of the rock where the TH divided by Y ratio exceeds 0.26, and we can see other portions of the rock where the ratio is less than 0.26. We can define, if required, this kind of rock belonging to zone C1 and this kind of rock belonging to zone C2. After that, once we look into zone C1, we can define subzone C1-1, and this is the way to write subzone C1-2. This is subzone C1-3. Students have to remember C1-1, C1-2, C1-3 can represent the different subzones which are the divisions of a specific zone. So here Mg more than 4.2, in subzone C1-2 Mg is less than 4.2, and in subzone C1-3 Mg is again less than 4.2. So you can raise a question, what is the need of creating C12 subzone and the C13 subzone, because Mg wise they are the same. The reason is that in C12 subzone Th by Ta is less than 10, whereas in subzone C1-3 Th by Ta is more than 10. Now the subzones can be divided. Let us divide this subzone. Now comes the division C1-to small a. This is a division of the subzone C1-2. What is so typical here? Here the NB divided by YB exceeds 6.22, whereas for division C1-2B, NB divided by YB is less than 6.22. So in this way, the different zones, subzones and divisions can be made. Further, let us consider only this one. From this division, subdivisions can be created. In what way this division can be divided is that NB divided by YB ratio. Now this division C1-B can further be divided if we decide that certain elemental ratio will be useful. In that case, C1-2B Roman 1 can be used and C1-2B Roman 2, and in this way the different subdivisions can be represented by alphabets and numbers. as zone C1 was defined, zone C2 can be defined by Th by y less than 0.26, and here we can define subzones C2-1 and subzone C2-2 in this way, that y by Ta less than 32.5 for this one, and for C2-2 y by Ta can be more than 32.5. This was just a specific example from a specific rock type. It does not mean that all the sedimentary rocks or all the reservoir rocks will be used in this scheme. Depends on what kind of chemical data we get and how we can group them. So, trying to understand the principle that the two zones were divided based on one elemental ratio, whether it is less than something or more than something, and then each of the zones were divided with the similar principle. When we were defining the subzones from the zone C1, we have used the ratio Th by Ta, whether less than 10 or more than 10, and the Mg value. Interestingly, when the other subzone was defined, C2-1 and C2-2, we were not using Mg Th by Ta, rather we have used another ratio y divided by Ta. This is important. While dividing the subzones, in this side we have taken care of y by Ta, whereas here we have taken care of Th by Ta. This is to be clearly understood. The second thing to remember is how the numberings are done, zone C1, C2, then the subzones C1-1, C1-2, etc., C2-1, C2-2, etc., then the division C1-2A, C1-2B, and from division, if we go on defining the subdivisions, it is C1-2B Roman 1, C1-2B Roman 2. So, if I take this short form of a presentation of a subdivision, this means here this 4 represents the subdivision, C represents the division, 3 represents the subzone, and 5 represents the zone. Students need to remember this way of numbering. Another important point is to be understood. Suppose this is a vertical rock column consisting of chemozones A, B and C. Chemozones A and B can be defined based on the elemental ratio, say x is to y. X can be any element, y can be any suitable element. Either it is more than A or less than A. So, in that way A and B has been defined. Now, this point can be used once again if x divided by y is less than A, we will define a chemozone C. So, it is not that x divided by y ratio more than A and less than A will define the two zones, rather just using this concept we can define more than two zones also. And similarly, by using the ratio P is to Q, whether more than B or less than B, we can define more than two subzones. Similarly, M is to N elemental ratio, more than C or less than C, we can define more than two divisions, and taking the ratios M0 is to N0, the two elements, suppose whether it is less than D and more than D, we can also define more than two subdivisions. This is a chemostratigraphic zonation given for a well where the SI by AL ratio, Mg% Ca% AL% Ca by AL ratio, Th by Y ratio, Th by Cr ratio, Th by Ta ratio, Y by Ta, Nb by Y and Nb by Yb are plotted. Here is a GR values and the depths are given. The different formations are presented here. I am not asking you to remember the graph or the formation names, just to show how the graphs together appear in case of a real data set. And now here different divisions, subdivisions, zones etc. have been defined. You can follow this number C1-1, C1-2, C1-3 and C1-4, C2-1b, C2-C1, then C1-2 and C1-4. I would request students that when TAs provide you the slides, you take a color print in A3 size paper and see in detail. C13A unit is interesting. Here it shows that the Nb by Yb ratio falls. Same fall is observed for Nb by Y ratio. In case of Y by Ta, there is a fall. For other ratios also we are observing sharp decline, but here Th by Y is an increase. Here is a decrease, sharp increase, a continuous fall. Here there is no such changes, the thing is mg percent wise, and here in SI by AL there is a drastic fall. Most of the elemental ratios have given a fall, and based on that C1 3A has been defined. For the other units, are you able to see interesting changes in the ratios or in the percentages? That is why I am asking you to take color print in A3 size paper and see in detail. Not all the ratios will show increase or decrease, but most of the ratios can show increase or decrease patterns.